Welcome to the next episode of the YugabyteDB Friday Tech Talk. Sorry, we had some technical glitches that took a while to get started. We just were slow to go live. I think the Zoom, LinkedIn setup, I don't exactly know the reason, but apologies for that. Welcome all. My name is Kannan Muthukkaruppan, one of the co-founders at Yugabyte. And my pleasure to welcome Taylor Vesely to this YugabyteDB Friday Tech Talk by engineers for engineers. So without further ado, Taylor, take it over. It would be great if you could do a brief introduction about yourself and then introduce the topic.
Yeah, I'm Taylor Vesely. I'm a software engineer on the YugabyteDB LRT team. I was previously the support architect, and I've been working on the development team for about a year now. I've been at YugabyteDB for 3 years, and it's been very cool. So today I'm going to be talking about how to monitor transactions and locks in YugabyteDB. We've got a bunch of new features that we've added to Yugabyte, and they allow you to monitor transactions and locks. So first off, YugabyteDB is distributed Postgres. We support 3 transaction isolation levels. Read committed. It's the basic isolation. It doesn't preserve consistent reads, but it's the default isolation level in Postgres. And this actually is new. We haven't supported read committed until recently. We also support repeatable read. This ensures consistent reads within a transaction. And serializable, it's highest isolation and guarantees sequential transaction execution. We also have 2 concurrency control modes. We have a new control mode, wait on conflict. So a transaction waits for conflicting transactions to finish in the queue. And then if there are no conflicting transactions, the write can go ahead. And then we have fail on conflict, which has 2 transactions conflicting. The highest priority transaction will either be wounded or die. And it's best effort for retries.
And maybe Taylor on the previous slide. I just wanted to add one more color. The wait on conflict also is a fairly new feature, and I think you'll get to maybe which release and so on. But one thing I wanted to say is it fair to say that even though you say no transaction priorities, maybe one way to think of it is it is kind of, because it's a queue, it's a first in, first out type of priority model.
Right.
Yeah.
Yes.
All right. Thank you.
So yeah, it's first in, first out.
Yeah. So there's an implicit priority is what I'm trying to.
Yes. So let's talk about the life cycle of a write real quick. I'm going to introduce how we do a write, what it does, and what happens if there's a conflict, so that we can have an idea of when we get around to looking at the distributed transaction locking features, the visibility features, that we know what to look for and why we're using it. So first off, a client starts a write request, and then the back end processes and routes this request to a T server. Then the potential conflicts are identified and resolved. And finally, data is written to the intent DB, which is where we have our provision. We store intents or provisional rights that, should the transaction commit, will be visible to other transactions. So just to get an idea of that, say we do an update on the table foo. The Postgres backend will send that write request to a T server, which will begin a transaction, route a write operation to the correct tablet, where it will do conflict resolution with potentially conflicting transactions, And then if wait queues are enabled and there's a conflicting transaction in flight, it'll be placed in the wait queue, and it can go through conflict resolution again. Otherwise, if the transaction has a conflict, it will send a conflict error back to the Postgres process. So we have two of those conflict resolution modes. Fail on conflict is the first one. And so if a statement fails with a conflict error, it will restart the current statement from the beginning without sending that conflict error back to the client. And in fail on conflict, we have wound and die. Wound is if your transaction is the higher priority transaction, it will wound the existing transaction, canceling that transaction, and you can perform your write. If you are the lower priority transaction, then you die and you get your conflict sent back to the Postgres backend. So the priority can be customized by a GUC. We have two GUCs, the transaction priority upper and lower bound, that says, where is my range for this transaction? So your transaction will get a priority between 0 and 1. And then when it arrives at the T server, the one with the higher value wins. And
in case people aren't familiar with the GUC or GUC terminology, maybe you should just clarify.
Oh, yeah. So GUC is Grand Unified Configuration in Postgres. It's a session level setting that you can set as part of your client when you connect, or per statement that lets you control something in the Postgres backend.
Yeah, I mean, yeah, and these are, I would say, fairly advanced knobs that most typical users shouldn't have to set. And if you really need, that I just caveated, like, it sometimes seems like people might get concerned, like, oh, do we have to understand and configure all these variables? But that's not really the case.
Yeah, if you have a really high priority transaction, that's when you might really need to set this.
Exactly. Yeah.
And then we will retry. Should there be a conflict error, we will retry with an exponential backoff. So it'll retry the statement several times over, and then from the top, planning, execution, all of it will retry with an exponential backoff. And so I think it starts with like 5 milliseconds and goes from there.
Yeah.
So you don't have a wait queue in this mode. And if there's no conflicting transactions, you can perform your write. However, should you go through conflict resolution and have a conflict, the conflict is returned back to the Postgres backend, which from there, it will retry. Notice that nothing is sent back to the client at this point. It will retry the statement from the beginning, and it will do that, I believe, a default of 20 times before it will return a conflict, unless you're in read committed, which it will do this indefinitely.
And Taylor, there's a question coming on the channel, which is like, what happens if the priorities of two transactions are the same?
I think that the existing transaction wins in that case, but it's a floating point number, so it's unlikely that there's actually going to be a collision there.
Yeah, and my guess is it's in the rare event that there's a collision, there is it's almost the app shouldn't care which one is picked as the winner, right?
Right.
So it should allow the system to make a decision in the case of breaking the tie.
Right. Yeah, but I'm relatively certain that the existing transaction wins in that case.
Okay, thank you.
So, and then we have a second conflict resolution mode, wait on conflict. This is new as of, I think, 2.19. And now, rather than all of the retry logic being embedded in the Postgres process, we have a wait queue for incoming transactions, first in, first out. So they're placed in the wait queue until the conflicting operation is either committed or aborted. And when conflicting transactions finished, the oldest transaction in the queue repeats conflict resolution. And in the case of a conflict with, say that your conflicting transaction committed, well, now you have to restart from the beginning, pick a new read point, and try again.
Yeah, because these two transactions could have been trying to, say, increment the counter on a particular row.
Right.
So the other transaction got ahead and changed the counter from 5 to 6, and you were planning to also increment it by 1. You need to reread the new value 6. So that's why you have to retry with the new read point. Yeah, thanks, Taylor. Makes sense.
And in this mode, because you've already waited in the wait queue, we don't have an exponential back off. It just retries the statement immediately.
Yeah. So in general, with the wait on queue approach, there is a lot less, especially if you're using it in combination with read committed transactions. You might be in the middle of a multi-step transaction, which having already done 2 or 3 DML operations, and your fourth statement. With the wait on queue approach, the nice thing is you just have to retry that fourth statement in read committed mode, and you can keep making progress. And yeah.
Yep. So again, we're coming in with a new transaction, but this time when we find our conflicting transaction, we enter the wait queue here on the tablet server. Then say that the existing transaction aborts, then we just go and do our write as initially planned. But let's say that your transaction hits the existing transaction commits. Well, then we'll return a conflict back to Postgres, and just like in fail on conflict or the other conflict resolution mode, we'll restart the statement. And this happens by default 20 times, I believe, before returning a conflict error back to the client in repeatable read and serializable. And in read committed, this will happen again indefinitely or until the statement timeout occurs. So yes, 20 times by default, that is controlled by this guck. Yeah, just again, we retry indefinitely in read committed. It only retries the first statement of transaction, and statement retries and queuing can look like hung backends. So we need something to be able to observe what is happening. So you can query.
Yeah, no, sorry, go ahead, please.
So we have 2 views into what is actively happening on the system that you can use that are new in 2.19.1. PG locks and PG stat activity is not new, but we've added some new fields as of 2.19.1 to make it easier for you to observe. And we'll get into that in a minute. So let's say
just if you would stay on the previous slide for a minute, Taylor, there's a question coming in. Yeah, and I think the 4th bullet here, statement retries and queues can look like hung backends. And now we're going to get into the main portion of the talk, which is like how to observe, which statement is holding the lock, and is there a cycle, things like that, right? But the question coming in is Taylor, is how does the conflict resolution work across these servers? is transaction priority defined globally or at a T server level?
I believe that it is selected at the Postgres backend, the priority. It's the conflict is checked in each individual tablet or shard. And if any one of those has a conflict, that's when you restart the entire statement from the beginning. And so it will go through conflict resolution in every tablet involved in the query.
And that's exactly right. Maybe just to describe it another way, yeah, the transaction priority question is every transaction's priority is kind of decided by the connection of the Postgres backend you connect to when you begin a transaction, right? And it also depends on if you can override it with a GUC setting, but by default, a priority gets picked for that transaction. But that transaction may update 10 rows. 3 could be on T server 1, another 2 could be on T server 2. So this decision of is some other transaction changing a particular row will be made as this transaction is going through like different T servers and when it's trying to update a particular record. So it, in a way, it works across T servers, because if 2 transactions are conflicting on a particular row, they're both going to have to visit that record, which may live on some T server. Yeah, go ahead.
So now you've got a statement that's hanging. It's just sitting around and it's not making progress. You want to find out what's blocking the query. You need to find out, hey, what's its transaction ID? It has to say, what is the query that is running? And give me 30 seconds. My speakers just went out. Sorry. How do I change this?
Sorry, what? I can hear you. Sorry, what did you say, Taylor? Are you able to hear us?
Give me 30 seconds. I'm sorry.
Yeah, no problem.
Would you say something, Kannan, now?
Hello, can you hear me?
Yes. Sorry about that.
No worries.
All right. So you need to know what node is it running on, what query is it running. So we've adapted PG locks from Postgres for Yugabyte, and we've added 2 new columns, wait end, YB details. It has all of the original columns, but we have 2 new columns. And also a 3rd new column, wait start, which is actually in Postgres 13. Yugabyte is currently running at Postgres 10, so we haven't picked that up yet. So we've added that in early. We've added in wait end for when the transaction stopped waiting and was written, and YB details has additional information needed for troubleshooting your given transaction that's Yugabyte specific. So yeah, we have all of the Postgres schema fields. So we're trying to focus on finding long-running transactions, and we want to figure out things like the transaction ID, min transaction age. We need to be able to intervene safely with conflicting transactions. So we can use something like YB cancel transaction, for example, to cancel a transaction by transaction ID. Because think about this, your backend could be on any one of hundreds of nodes potentially. And if you needed to go and send a signal to that exact backend, it's difficult to track down the node that you're on, what query is running. So you need to be able to cancel a transaction from anywhere. So we're trying to address specific use cases, like when diagnosing lock contention, finding consistency and performance problems, and identifying the individual query that is causing issues. And so we wanted to focus on usability. We want to be able to get a cluster-wide lock status and be able to diagnose the individual sessions that are broken or hung and be able to understand actually what is happening. So here is PG-Lock's view. Here are all of the columns relevant to Yugabyte. You have your lock type. You have the database the lock is being held in. You have the relation that is being locked. You have the lock mode, and strong read, strong write means that this is the actual record being written and not an ancestor of that write. You have whether the transaction has been granted and has been written to the IntentsDB or whether it's waiting. You have fast path for single shard transactions. You have wait start for when the transaction began waiting. And that's filled in if the lock hasn't been granted yet. And then you have wait end for when the actual record was written. And then you have in YB details, all of the details that help you identify things like which transaction is this running, what node is it on, what tablet has the lock, what column has been locked.
Taylor, could you explain the wait end one more time? Let's say I am interested in locking a row to do an x equals x plus 1, but somebody else has that lock right now. What would I expect to see in wait end?
It will be null until the lock is granted.
Okay, but if the lock is granted, then
it has been written to the IntentsDB.
Got it. Okay, the lock is granted, but that transaction has not finished.
Right, it hasn't committed or reported.
Got it. So the wait end would show the time that the lock has been granted to the other person.
Right.
But it doesn't mean when your wait is going to end. Like, okay, got it.
No.
Yeah.
It's when the transaction has finished waiting and has been written.
Got it.
Sorry if I wasn't clear about that.
And this is basically it's like this is the person right now holding the lock, and only when they commit finally they could be committing after doing 2 more DML statements on unrelated rows, and when they commit, then this all thing clears up.
Yep.
Understood.
You have the blocked by field. So if this is a in-flight transaction that is waiting on another transaction to abort or commit, you will see the transaction ID of that blocking transaction here.
So this is essentially the pointers to other like I am depending on transaction B, but this will tell me if this particular transaction B is dependent on C.
That's right.
Got it.
So, and you have the columns, the key, the doc key that has been locked, and then any columns that are being written. So as you can see, this is a lock on an individual column. So this is a write that has happened on an individual column in this table, column 2. The @num is the Postgres column ID in PG attribute. So you can use that to help you identify which column is being written. And then column ID is actually the docdb column ID, which can be different than your actual column being locked. And then whether or not we are locking multiple rows with this particular lock, say you got a lock on the primary key for something, well, that's going to lock multiple different columns or multiple, I'm sorry, multiple different, say that you got, sorry, I should say you get a lock on the prefix. Say that there are two columns. You've got the hash prefix and then the range prefix. So you can actually get a lock on the entire hash. And so that would actually lock any rows that are in the range prefix. Does that, I hope that makes sense.
I think when you get to the demo, maybe it'll be clear. And one thing I'm hoping, there's a question coming in, and you can clarify if you'll cover that in the demo. The question is like, what is the situation we can see a deadlock, and you know, is there, or does the conflict resolution rule out, you know, in fact, out deadlocks, but does it rule out deadlocks by the time this view is generated? No, in fact, deadlocks can happen, and I think you're going to talk about how to look at that in your demo, if I'm not mistaken.
Right. We do have a deadlock detector that runs periodically. When you see this, you can identify a deadlock, but more often than not, if the deadlock has happened, it will already have been resolved, and it will have canceled one of the transactions by the time that you get to this point.
That's because Yugabyte automatically does deadlock detection, is what
Right.
you point. Yeah. So that's interesting. So before you try to observe deadlock, Yugabyte's already handled it for you. But maybe there is a knob where we can slow down Yugabyte deadlock detection, if you, right? Anyway, we'll cover that.
Yeah, that's a good point. I'll think about how to do that for demonstrating what a deadlock actually looks like.
Yeah. Yeah, let's keep going. There
All
was
right.
just there was another comment which just said, if I understand this, you can use YSQL shell to find the waiters and blockers and potentially query a lock train or a lock tree. And if so, that's really cool. I mean, I think
Yep.
that's basically it. Yeah, you can figure out who is holding the lock that you are interested in, which node is that running on, what is the query text, and so on. Right? Yeah, go ahead.
And you can identify which columns are involved and which rows are involved. So it's all that information is available to you cluster wide. All right. So let's run a few queries. So I'm going to create a table with the primary key A and a second column B. And I'm going to insert a row into foo. So now we have a new table with one value, but I have started a transaction. It hasn't committed yet. So this is only visible from within this transaction, this row that we have written. So it's currently residing in the intent DB. And so we can query PG logs, and we can see our two locks. We have a relation level lock that's actually on the full tablet, because this is an ancestor of the write that we have performed to the intent DB. And then we have our row level lock with the strong read, strong write. This is the actual value being written. And we've written the entire row because this is a packed row where we've encoded all of the column data onto the same record. And this is enabled by default as of 2.19, I believe, is packed rows. Otherwise, you would see each individual column that we have written as individual writes. So let's just look at this another way. Let's cut this down. So you can see that we have our row lock, strong read, strong write. It's this transaction on foo. So we can commit that transaction. And we can select from foo. It's still there, but now because we've committed, it's visible everywhere to any new transaction in the cluster. So if we look in PG locks, there are no more locks because we've flushed this out of the intent DB. It's no longer a provisional write, it's a real write, and it's visible everywhere. So again, let's update our row. Let's begin another transaction and update that column that we just, that row that we just wrote. We'll set B to 2 where A is 1. So now within our transaction, B is 2 when previously it was 1. And if we select from PG locks again, now you can see that we've written a single record to one of the columns. So that is this value, because this is an update, not an initial write. It's not a packed row. We actually just write the new value to the column. So I can abort this transaction. And if I select star from foo again, you can see that it's back to its initial value. And when I run and select from PG locks again, there are no more locks being held. So, and in case I wasn't entirely clear, locks in Yugabyte are represented by actual writes to a docdb database called the intent DB. And so when you're
just to give our listeners some insight, it's like these are not in-memory locks. They need to be persisted, especially when for multi-step transactions, because it's a resilient system. It has to handle the failure of nodes, and that's why the locks are also kind of raft replicated and so on. Yeah.
Correct.
These intents, yeah.
So even if the node that is holding the lock goes down, if you query this table, you'll still see the lock because the node that takes over will have written this lock. So we can now, let's just do a delete. So now if we select from foo, there are no rows. And this is, again, in its own transaction. So then we can look at PG locks again. And you can see that we've done a strong write, strong read on the row. And this is the tombstone record that we've written to the intent DB. So we intend to delete this row. That's what we've written, is our intention to do that. So if we abort that again, and we select, of course, our row will still be there. We can still see it. And then if we select again, again, the locks are no longer being held. So what happens if you have a conflict? So let's run 2 parallel sessions. So over here, I'm going to update and set B equals to 2 where A equals 1. And in another session, I'm going to set B equals 3 where A equals 1. Well, this is now hung because it's waiting in the wait queue for this query to go through. So if we select from PG locks again, and this time I'm also querying the node and blocked by from our YB details. So we can see that this write has been granted. And actually, let me add wait start and wait end so you can see that. I know that it's kind of hard to see. Let me remove just a couple of fields so it's easier to see. So you can see that this write started waiting at this time, and this one was written at this time. So it's a few seconds between this started waiting. So let's figure out what statement is being run here, and then cancel our transaction to let this one go through. So if we can.
By the way, one small question, Taylor, for the rows that have wait end, why don't we also show the wait start?
It's because the way that we have wait end written, it's actually a value in our intent that is written.
Okay.
But we don't actually record the start time of our transaction as part of those blocks.
Okay.
So if we can, so pgstat activity is where you can see the individual transactions. Actually, first I'm going to expand the view, then I'll look at this. So let's give it the transaction ID of the session that we're being blocked by. So we can see now that the session that is blocking the other session is actually us. I'm within the transaction that is blocking this other transaction. But what happens if we were on another node? So here I'm on a different node in the cluster, and I can select from pgstat activity. I don't see this backend ID. It's not there. And that's because let me just take the where out. There are only two sessions currently connected to this node, the one that I'm on, the one that just selected this, and our hung statement. So as part of PG locks, we actually can get the node ID of, so we can actually get the node ID of the node holding the lock.
That's the blocked by column.
It's actually yes. So this.
Oh yeah, the node holding the lock, and that in turn is blocked by somebody else. Yeah.
Right. No, it's select star from YB servers. So now we can see node A80 is actually a different node. So you can then go to that node and query for that transaction ID to see what query is or what that session is currently running, the last statement that it ran, and whether is it idle in transaction or is it active? What's going on there?
Yeah.
So now say that you're on another node and you just want to get rid of the transaction. Well, you can run a YB cancel transaction against that transaction ID. So the one that's blocking is EF here. and I can say YB cancel transaction. And we can go back to our other session, and you can see that immediately that that session that was blocked has gone through. And if we go back to our initial session and we say, we can see that our transaction was aborted.
Yeah. Very cool. We are a little bit over time already. I know we started a little late. Are we almost there, Taylor? What, any closing?
Well, that was the end.
Awesome. Yeah. Did you have any other slides or anything you wanted to cover, or we're good?
Nope. Well, there is one more slide.
Okay.
So what happens if your locks don't show up? So we actually filter the queries that PG locks will show according to these two gucks. So the intent of PG locks is to be diagnosing lock contention in human time. It's not especially useful for diagnosing locks on the fly. That's what the back end is doing. So if you've got something hung, you need to we want to be able to filter, and also to avoid querying every table in the entire cluster for every lock. We only want to be seeing the transactions that are fulfilling certain criteria, namely, if you've got something that has been running for a really long time, you want to see that. You don't want to see something that's been running for 3 milliseconds. So we have YBLocks min transaction age to help filter that. And in order to prevent querying every transaction in the entire cluster, we have YBLocks max transactions to limit how many transactions we will actually return.
Yeah.
So
and these are of course changeable, but designed in a way to help you diagnose the most common problems where locks are being held for long, or there's like something unexpected happening in the system.
Right. And thank you.
Wonderful. There's one other question which says, do these locks show both server level and engine level locks in the same view? I'm coming from MySQL and I recollect separate views for server and InnoDB engine locks. I don't think we distinguish. I mean, it's like, but Taylor, you're free to answer the question.
Yeah, I don't think that we have the same distinction.
Yeah.
It's comparing apples and oranges. We have our locks. We do technically have short-lived in-memory locks and things like that, but even in Postgres, you don't really get a view of those. So, yeah, that's it.
Yeah. Thank you all so much for joining. Again, sorry about the technical glitches at the beginning that had caused the delay. And see you all next week on another episode of the Friday Tech Talks. Have a good rest of the day and weekend. And Taylor, over to you for closing comments as well.
Yeah, thank you very much. You can reach me on LinkedIn for any questions. Taylor Vesely.
Yeah. Thank you, Taylor.